I'll just move on.
Yeah. Okay. Y'all can hear me. The transcription is going. I don't know why it said I don't know what you call baby. That's weird. We're not gonna look at that.
He called you baby?
No, the transcription said that.
Yeah.
Not me. But whatever. It's fine.
Okay.
We're gonna move on.
How do you think I?
All right, guys. So
Oh, yeah, I think that was. No,
to start off, y'all simmer down.
Oh, I said.
Just simmer down. So first I'm going to talk about the first part of the exam. So the first part of the exam is going to be 20 multiple choice questions, closed book, closed notes. So what's going to happen if he hasn't already said this? You are not going to have anything out. You're just going to be handed your part A of the exam. All you're going to have out is a pencil or a pen if you feel really confident. And then you will take part A, and then after part A is done, you are going to turn that in, and then you can get your calculator out, you can get your all your materials, you can get your computer out, etc., etc. And just a few, like, I can't tell you exactly what's going to be on it because it doesn't change much year to year. I can tell you that you need to focus on concepts. So there aren't going to be anything that you need a calculator for. So there's not going to be any math. It's going to be like, think about the passive and active elements that y'all have learned about so far. Resistors, sources, dependent sources, inductors, capacitors. Think about how they work. Think about what are their properties. Stuff like that. Think about your KVL and KCL. What do those mean? How do you use them? Or what, like fundamentally, what do they mean? Things like that. Think very fundamentals, but no matter what, don't spend too much time on part A. It is 20% of your grade, so each problem is worth 1 point. If you get stuck, if you don't know, circle an answer and move on. Unless you really thinking about it for a little while is going to help you remember, it is a lot more important to get to the rest of the test because it's going to be 4 questions and you want to make sure that you finish the test.
But didn't you say that we should make sure that we actually put something?
Yeah.
It was just 1 point for correct, 0 for not correct, -1.
Negative one or not?
I think, I mean, I don't know if he was actually joking, but that's what he said.
Yeah, it was something like that. It was some, it was some,
He sounded pretty serious.
He did.
Yeah.
He sounded pretty serious.
yeah.
Okay, then yeah, circle something. You got a 25% chance if you're feeling lucky. You might get it right anyway.
On like the level of concepts, are we talking C plus A plus T spells cat level of concepts or?
It depends on the question.
Yeah.
So, electronics, there's a lot more like, what's the formula for this? But for circuits, some of them are pretty easy, some of them are pretty common sense.
Yeah.
Some of them, there will be a couple that are thinkers, a couple that are harder. It's kind of a mixed bag, but none of them are like groundbreaking. None of them are super duper hard. At least they haven't been in the past. He might throw a curveball on there, but like I said, don't sweat it. Don't sweat that specific problem on the test. Review your concepts, but otherwise, yeah. So that's kind of general part A knowledge. I can't prepare you too much for it otherwise. Are there any questions about that otherwise? So it's not time-based, it's however much time you want to spend on it. So as soon as you're done, you turn it in and then you get part 2. So it's up to you. And that's why I said, if you're stuck on it, don't spend too much time so that you can turn it in and start on part 2.
Oh.
Right? Cool. Otherwise, comments, questions, concerns? Good stuff. So, as for what's going to be on this test, I haven't gotten any information more than what y'all have got. And so he said the things that can be on that test are basically everything you've covered so far. If you think about it, I highly doubt there's going to be like a resistor combination on there. I highly doubt there's going to be like at this point, even like a capacitor inductor combination on there, since you had those already and y'all did really good on those. Well, you didn't do great on the resistor combination one because it was kind of weird, but that's okay. So what's probably going to be on there, source dominance, know it, but I would be surprised if source dominance was on there. Think Thevenins and Nortons, high probability of that'll be on there. Something using MAME and name is indubitably going to be on it. Whether it's name and MAME doing Thevenins and Nortons, name and MAME complex impedances, name and MAME on a first order network. So if you are unsure of how to do the matrices, if you're trying to write out equations still, come see me. Let's make sure that we have the MAME and name solid. As for, like I said, complex impedances, high probability. That was the lowest so far. Like I said, I still have a couple more to grade. I wanted to give them back to y'all. And then that was the lowest on test 1 and 2. Out of test 1 and 2 was the complex impedance problem. And then first order, something is going to be on there. Whether it's something like this, where it's like a switch, or if it's, well, there probably will be a switch problem. And otherwise, kind of a toss-up. Like I said, there's going to be 4 questions. Yeah, I don't know how much else I can say on what's specifically going to be on there, and I apologize for that. But just make sure you know the simpler things, the combinations, and also maybe for part A, how resistors combine, how capacitors and inductors combine. That might be on there. Oh. I honestly don't remember. That's one I don't know. But that could be on there. So know those things, even if it isn't for part 2, it might be on part 1.
I do have a question. So for those four free response question, well, not free response, but
Mhm.
yeah, you know what I mean.
Yeah.
How much time do you think it will take on average on each problem?
It depends on what you would consider yourself like better at.
Okay.
So if it's just like a Thevenins and Nortons and you feel pretty confident, you can probably knock that out with a MAME or name and then
Okay.
solve it in your calculator.
Okay.
The resistor, like these types of problems, the complex emittance problems can be harder for some people, so those might take longer. It's really about time management.
Okay.
So you'll take like maybe 20 minutes to do part 1, if that. If you can get it done in 10 minutes, 15 minutes, that's even better. How long do y'all have for your final? Is it 2 hours or 2.5?
Is it like, how often do people have to take the entire time? Is it very rare that people take the entirety of the time? No? Okay.
I will say that most people take the whole time. It's people, like more people will turn it in before the time is up than the other tests, but it's definitely people will take the whole time. So time management, don't spend 45 minutes on, try not to spend 45 minutes on one problem. If you feel like you're struggling, move on to the next one. Go through the whole test first, figure out what you're comfortable with and do that first. It's better also to do almost all of the problems than it is to do 2 of the problems fully. Think about partial credit. I try to give as much partial credit as I can. Think about it that way.
Thank Bryce.
I try. But other than that, for like general test taking strategies, that's about all I have. And then someone was asking if it was recorded. It is recorded. I promise. And so, yeah, otherwise, like, it's really a strategy game. Figure out it's how to take a test. But y'all will do great. I believe in y'all. So, before I head over to the first order stuff, does anybody have any questions, anything specific they want me to go over?
The last problem, this problem said would be very nice, because he didn't actually give a full-on answer to that one.
Yeah, I don't know if you have the solution, so I think it's 1.186, right?
I just know it was the last one of this problem. I can say,
I do
out of
do
the
the
first 5, it was the last one. The 5th one. So I guess the 5th one.
This one?
Yeah,
Yeah, that
the
one.
complex admittance one.
Okay, it's not on the answers part B.
Correct. Yeah, so he said that one ran away.
Yeah.
This one,
I mean,
that's right.
And then he.
He set it up, but he didn't.
Oh, all right.
Okay, we can definitely look at it, but I am not gonna lie, this stuff is for a lot of the upperclassmen out of sight, out of mind, because you figure out a much easier way to solve this starting in circuits 2. And so the rise and fall time, the like switch conceptually, we all remember, and that's what I'm gonna go over. But
Tell us the secret, right?
thank you, Francis.
Yeah, it's Francis.
Is that going on the Instagram? Oh, cool. It'll be an event. But
Yeah, my good side, friends. Yes. Let me stick in my stomach, okay? Just let me know.
I was surprised when-
sorry, I got distracted.
What did you say, Chris? Pay attention.
Oh, yeah, hold on.
I got distracted,
Okay,
sorry.
Paying attention by Fred.
Francis, you're distracting it.
I'm just here to grab 2 locators, okay? That's it.
Okay.
Yeah.
And so I was gonna say, we're gonna go through it and I'm gonna make sure it's right with the solutions, and I don't want to leave y'all wrong. So we can set it up, we can look at how you would solve it, but I think it would be worse for me to solve it and me be unsure. So we're gonna try to nail in the concepts and make sure it's right. Was my plan. If that sounds good with y'all.
Yeah, I just wanted to know, like, just to be sure, we're allowed to use our old exams and our notes during the second part of the exam, right? Okay.
Yeah. Yeah, that was why I really wanted to get exam 2 back to y'all if I could. Sorry.
Has he posted, solutions for the extension? Yeah. He posted a long time ago. Yeah.
Yeah.
Then yes, he has.
Cool.
And yeah, you can use any of the solutions, anything like that, that'll help you out. Just, don't communicate with anybody. Don't text anybody on your computer. That would be really appreciated.
Don't post the question on Shag.
Don't post it on Chegg. Don't do any of that because once that happens, it ruins it for everybody else. So
If I have to take this final more than once, we're gonna have a problem.
y'all, I think y'all will be good. And
The lenient easy version first, you're not gonna do.
what I also want to say is, don't worry about your grade too much. If y'all are getting lower grades, if y'all have a lower grade on the midterms, don't stress about it too much. He doesn't officially curve anymore. He doesn't do his bell curve, but what I can say is if 60% of the class isn't getting a C or 50% or even 40% isn't getting a C, we're not,
You're not.
you
gonna
catch
finish.
my drift, right? I'll catch my drift. Y'all are gonna be okay.
Yeah,
Don't stress about it too much. Don't stress about your grade. Try to understand, try to work through the problems, try to get the concepts down. That's what it's the big thing that I want to say because it will help you with circuits too. It will help you with electronics. That's more important than getting a good grade specifically in this class.
Is your computer back again?
It is charging.
Okay.
Yep. Appreciate it though.
In the content are cool, and everything, but I'm not sure it is more money.
Hmm?
In the content are cool and everything, but I'm not trying to waste more money by repeating it. No, fair.
But what I'm saying is you're gonna be okay. You're gonna be okay. So, active elements. How do y'all feel about them?
Good.
Okay, I'm gonna ask some questions.
And like voltage sources and current sources.
No. Like, let's ask this. Again, just gonna go over some conceptual stuff. At steady state, what does a capacitor look like? Does everybody agree?
Current flowing through.
Mm-hmm. And you can think about it, it's an open circuit because of, there's two plates, right? Yeah. There's not gonna be current flowing between the two plates when it's just, charges built up on two plates. So whenever it's a steady state, it looks like an open circuit because there's no current flowing through it. On the other side, at steady state, what does an inductor look like?
or circle?
Exactly. Because in reality, it's just a wire. If you can make an inductor by just like getting a PVC pipe and wrapping wire a bunch of times around it, and it makes an inductor. Yeah, it makes a magnetic field. So at steady state, it just allows all the current to flow through it. Now you can think about with AC current, one, it's the exact opposite. So that's easy to remember, right? So a capacitor looks like a short circuit. And that's because there isn't the time to build up the charges yet. So the physics department would say there's not charges flowing. There's not actually charges flowing between the plates. It's more that the charges are being pushed up and then pushed down as the charges are building. So it looks like a short circuit. The electrical engineering department is saying, yes, because there's no charges built up yet, the current just flows back and forth. That's the convoluted way to say.
We are.
In electrical engineering, of course we're right.
Yeah, we are.
From a strictly physical perspective, it's more of the physics department.
We're starting.
And then
Like, come on, who really does physics? Really, come on. Okay.
Bunch
Uh,
of eggheads.
Pickard Hall.
Russ doesn't like that call.
He does not like Pickard Hall. Now, an inductor, like I said, the exact opposite. So an inductor looks like an open circuit. And this has to do with the magnetic field. So I'm a little shakier on the physics on this one, but it has to do with the field that's created when it's going back and forth.
Or, I mean, I guess you could think of it like, because inductors resist changes in current anyways.
Yeah.
So if it's constantly coming back and forth, you're not gonna get that current through either side of it.
Yeah, that is a really good way to think about it.
But I guess that's more of like engineering.
Yeah, and that's the engineering way to think about it. I don't really know the physics reason behind that one, but that's another really good point. He said inductors resist change in current. The dual of that is capacitors, which resist change in voltage. Does that make sense though? Okay. That gives me what I need to know. So you can memorize this as a fact that capacitors resist change in voltage. And inductors resist change in current. I have that written down on my cheat sheet. That was something I just wrote down. But again, from the capacitor side of things, you can think about it. Charges, once they build up, that creates a potential difference. That creates a voltage. So it's not going to want to change all of a sudden. And then that moves on to what capacitors and inductors look like. So since a capacitor resists change in voltage, it looks like a voltage source because it's supplying that voltage. And then that's why an inductor looks like a current source because it resists change in current, so it's supplying that current. It is that constant current that once things change, it has a current going through it that it's wanting to supply. Okay. How's everybody doing?
Gucci.
How's that side of the room doing? Are y'all kind of understanding this? Kind of? Okay. People who are understanding it, good job. People who aren't, what are your questions? Don't be scared. This is rough.
For me, when, for the first question of problem set 5,
Mhm.
how do you do the graphs?
Okay.
So basically part C.
Yeah. So you know that, and this is one of the things that is kind of just inherent about the active elements, especially capacitors. They're going to have an exponential relationship. And he says that a lot. It's always going to look like once it changes, it's going to look like this until it balances out. Really? Are you really going to freeze on me? I really don't appreciate that, computer. Okay. My point is, there we go. It looks like that until it balances out. And that is that resist in change. So the voltage is going to start out slowly changing or quickly changing and then balancing out eventually. That's just an inherent property that once it changes, it's going to change slowly. It won't change instantaneously. And that's what's going to create that curve. So as for how you draw it, a lot of that is going to have to do with your 90% and 10%. So you know that you're good. Pretty much this is gonna be your 10%, and this is gonna be your 90%. Um. So your rise time is your 90% minus your 10%, right? Correct me if I say anything wrong, please. That is going to be.
If we use that in the formula, right?
Mhm.
Whenever we make our, because I think in part B it says define our complete time domain expression. So with that expression, that's where we can figure out time rise, which is time two, minus T1, which is our.
Mhm.
And then we use that 10 and 90% to figure out the graph. How to write it down.
Exactly. And so that creates your, like, you have like this guy here. And then you have your like 90%. And then you have back to up here. And then it goes back up to the 100%. If that makes sense. So that's kind of
Oh, so the graph is just basically a concepts thing, right?
I
kind
think
of.
like Russell was talking about it, I could get it wrong, but didn't he say something like this right here is just saying that like if I were to flip a switch,
Hmm.
it would be like, that would be kind of like if we slowed everything down, because obviously like flipping a switch is like the speed of light, right? We know speed of light's pretty fast.
Hmm.
But if we were to like slow everything down and we would have flipped the switch, we would see that at the chart. Like as soon as we flip it, and then once it gets to the top, it's like all the way flipped.
Exactly. It's not that it's all the way flipped, it's balanced out.
Yeah.
So for a capacitor, it's gonna start at whatever voltage is at, it starts at. That was terrible. It's gonna start from whatever voltage it was at a long time, and then it's going to eventually balance out to either more or less than it was depending on the circuit.
It's like discharging or charging, right?
Exactly.
Okay.
It's always gonna kind of probably gonna have it be discharging. But
Oh, yeah.
Like whenever you did your test, did he make you write the graph out as well? Because I know like on our homework, whenever he uploaded the solutions, like looking at it, he didn't write them out.
How many do you even answer?
Yeah,
Yeah.
I don't think we have to write the graph.
Yeah, I don't think we're gonna have to.
I think that was just to help us visualize it.
Oh.
Yeah.
Question for the rise time though, I remember in class, we kind of derived an equation that in my mind, it sounded like he said this, you can use this for everything. Or just that, rise time equals tau times ln of 9.
mhm.
Is that for every single, like, is that rise time for every single circuit, or is that just like a? Yeah, I thought that was the general solution for every single circuit.
Before I say,
I mean, not every single circuit, but like the circuits that he was giving us, I thought we could use that.
yeah,
To find the rise time on basically all of the circuits.
yes.
Okay. Tau, so RC,
Yeah.
ln 9,
So either RC for an RC circuit or
GL.
Yeah.
or L1.
Well, I mean, it should work every time
Yeah.
because your rise time is I mean, of course, the time it takes to go from the 90 to 10.
Yeah.
But every time that you subtract them, like subtract the
Okay.
10 from the 90, you're gonna get tau times L in the 1.
Okay,
Mhm.
And so, I mean,
yeah, because on his solutions, he would give like time 1 and 2, which I know that's how you derive that thing, but some of them you just give like time 1, I'm like,
Exactly.
I don't know if this is what he was asking for, but okay.
So what that was is, so you know how in class we took the 90%, 10%,
Yeah.
found the voltage and solved for it?
Yeah.
So he's just doing that by steps. Yeah, that's all it was.
Well, some
That-
of them
that-
literally just
yeah.
time 1, those are.
Well,
that's what-
yeah, that was just him deriving natural log of 9 minus tau, gives you your rise time.
Gotcha.
Mhm.
But yeah, it's short, like circumventing all that deriving rise time times ln of 9 or 9 times
Yeah.
ln of 9.
Sweet.
Yeah, and then what you need to do to find exactly what T1 is you do tau times the ln of 1 over 0.9. You do tau times the ln of 1 over 0.1 to get your T1 and equals your T2. Should be right. And that just comes from deriving it. So then also, I'm realizing now, the graph comes from your VC graph. That's that equation. I understand now. So you have your first order comes out to be VC of T. So your M times your 1 minus E to the negative T over tau. Y'all remember that from lecture?
Yeah, that looked familiar.
Mm-hmm. So when you graph this, that's where you get that graph. And then you can take from this graph and plot exactly where this rise time is.
Oh, so that graph is basically this equation. right?
Yes.
Okay.
So this is your this is V max.
Okay.
This is V min. And then this is
That's
VC.
yeah, T equals infinity. Unity, zero.
Exactly. So let's look at the problem. Conceptual. Are there any more questions?
Doing the 1.104.
The very first.
The gross looking kind of long one. Did everybody have what I wrote down before I erase it?
Okay.
Cool. All of this. So this is a really big, scary looking circuit. What we're gonna do is reduce this down first, because this would be a pain in the butt
Yeah.
to.
Can we do this on the capacitors, right?
Yeah. So what we're gonna do first, we're gonna take this whole capacitor thing, because we know how to combine capacitors. And we're gonna get rid of that. So then what we're also gonna do, we see that we have this voltage source here. That, since we have this switch here, it is a lot easier to keep that branch the same. So what we're gonna do to allow us to have all of the same type of sources, it's easiest to transform this into a voltage source. So we can do definitely that. Pretty easy, right? What is this voltage source going to be?
5 volts.
Yep, exactly. We have 5 volts. What's the resistor going to be?
Okay.
Great. And then we have this switch. Resistor. This is ugly. And now, does someone want to do this combination really quick?
It ends up
30.
being
About 33.3.
nanofarads.
33.333 nanofarads. 33.3 repeating nanofarads.
I didn't say the bird.
My teacher. I'm supposed to make another for the capacity.
It's a great question.
What was the question? Polarization of capacitor doesn't matter. What are you talking about in terms of adding and subtracting?
Yeah,
And on the, solution set, just added them all up normally. So,
so since these are different, that's not gonna let me graph. Since these are different polarities, I'm gonna say no. It does not matter. Final answer. Which makes things a lot easier for us, right? So now we're looking at this. This doesn't close until time t equals 0. So what we're gonna do is first we are going to figure out what this looks like at t is equal to negative infinity and up until 0 minus. So when we're looking at this, do we need this at all?
It's just open.
Exactly. There is
Yeah, there's literally.
no current that's going to be flowing here. So for the sake of time, we can just get rid of all of this. Not that. But now this is a lot simpler. So we need the voltage from here to here. What's it going to be? How do we figure that out?
Anything from the last time this it all came down to, yeah, -5. Right, so those two don't be wrong. Yeah.
Because the question is, well, the first question is there going to be any voltage drop over this?
I'm thinking the 0 voltage end of the battery.
Well, it's been running for so long
Is
that.
that
I think there is.
That's not the reason.
No current.
Mhm.
Sorry, charge for a line.
Exactly. So if we know that this is an open circuit over here, that makes the circuit look like just, this isn't gonna like me. It just looks like this. So is there any voltage drop over this now? Exactly. So if there's no current, there's no voltage drop because V is equal to IR. So V is equal to literally anything times 0. Voltage is gonna be 0. I hope I'm not going too slow, by the way. I want to make sure that everybody has these concepts really down.
This is the final thing.
So what in this case is going to be the voltage over here? We said it earlier.
-5.
Exactly. So here to here equal to -5 volts. Sweet. So we have the graph that Russell does, right? So
Wait, so what's the reason why it's -5 volts again?
So we know that the voltage from here to here is 5 volts.
Uh-huh.
So to get to KVL, the sum of all the voltages
Mhm.
around this loop has to equal to 0.
Oh, okay.
So
So conservation of energy, right? Yeah,
mhm,
okay. Okay, that makes sense, yeah, I understand.
mhm. And what we can do, it's -5 volts. If we want to look at it from a KVL, we could see that in reality, it's going to be a positive and a negative here and just 5 volts. Because that means, say we can consider this ground because this is going to be 0 volts.
Okay,
So then we see that from another perspective, from here to ground, so from this red dot to ground,
Okay,
on this side, we have a voltage drop of 5 volts.
okay, okay.
Means we also have to have a voltage drop of 5 volts over here.
Oh, okay.
So that's another way that we can see that it has to be 5 volts with that polarity. Now, the reason I wrote -5 is because this V1 up here has the positive and the negative there. So I want to write the positive and negative because that's V1
Okay.
and it's my computer is crying. I have like a million tabs open. So that's why I did it like that.
Okay, okay.
So how do we feel at time is equal to negative infinity?
Yeah.
Pretty good?
I think I feel a much better about it.
Sweet. So the general rule is KVL and KCL always have to apply. So if we're looking at an inductor, I'm going to close this door. If we're looking at an inductor, it's going to be the exact opposite. Because it's going to be a short circuit. So when we're looking at KVL in a closed loop, we need to know that the voltage drops have to all add up to 0 and the current has to be the same. So we know that that current flowing through the inductor is going to be whatever the current is in the loop. And we also know that there's not going to be any voltage drop because it looks like a short circuit. So the voltage drop is going to be 0, and we know the current flowing through it is going to be whatever is determined by the rest of the circuit. We can look at another problem after this. We can look at what would happen if this was an inductor, like an inductive load. Because like the way that he set this up, this is really a load. He gave us essentially a capacitive load. So you can think of this equivalent capacitor as the load, and that might be what he gives you on the final. He might give you a load. All that means is that there is a terminal here and a terminal here, and there's something in between that is going to have a voltage drop or a current flowing through it of whatever we determine. And that's the problem. So this capacitive load, we can also look at it at an inductive load in a minute. But now we have T is equal to negative or 0 minus, not negative 0. So now let's look at whenever the switch closes.
At T equals 0, right?
Exactly.
Okay.
So we're going to still have the same circuit. Circuit's going to look basically the exact same, except there's the middle part. Exactly. So now it's just a wire. We can see these. That'll be a switch, closed switch, if y'all are good with that. Have our capacitor. Okay. I just had to go back and look because I forgot to say this earlier. Make sure you read the question. I am guilty of this. I know for like test 2, for example, one of the things on the instructions was to write out the full name. So if someone just did this minus this and they didn't write out the numbers, I can't give credit because that's not what the question asked for. So make sure you read the question. So now we know that the question is asking for, now that I've reread it, time the voltage at T is equal to 0 plus and T is equal to infinity. So that's what we're looking for right now. is the voltage gonna change from T 0 minus to T
0 plus no. I don't
0
think.
plus over the capacitor? Why not?
Easy answer.
That's all good.
That changing, the instantaneous changing.
That's the right answer.
Oh, okay.
It's gonna resist the change because that's, we know capacitors do. They don't want to change voltage instantaneously. The thing that will change is the current. So
I think the probably should just.
yeah, I was gonna say it's not asking for the current, but that is something that he could very easily ask. What is at T is equal to 0 plus the current? Not goose egg.
Not this-
Blanked out after the plus.
Be the
So
5 volts divided by the total load.
well, you got the other sources too.
You have to do source transformation, put them together,
Current sources.
and then do the impedance. Oh, yeah.
Current sources, I don't know. Go back to it.
You know what would be maybe kind of easier? Is if you just did a little MAME problem.
Russell tells us it's peanuts and sledgehammer.
Yeah. Give us it.
It depends on what you're more comfortable with, honestly. Is it overkill? Maybe, but if you don't feel great about finding out what the current is, and you feel really confident with a MAME and just doing 2 little loops, go for it. Because you know that the current is gonna be IM2, right? So on if it was just 1 loop, for sure. Don't waste too much time, but honestly, I would not want to make mistakes and I would use a sledgehammer for, what did he say, a nail?
Peanuts.
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 Overkill is underrated.
Get it right. Don't skip steps. If you don't feel comfortable, we can look at how, see how he did it. Yeah. So what did he do? Let's see. He did,
Well, if we're trying to find the current,
Yeah, I
Oh,
don't think.
I think we skipped the entire
He didn't-
thing.
he
He
didn't-
didn't do the.
he
Yeah.
didn't specifically ask for, it, but if he did, then like, for example, what's the current at 0 minus?
Mhm.
That's it right there. One minute.
but that's through, that's just finding the voltage. The current flowing through V1 is not negative 1 milliamp.
Because now we have that extra one.
Mhm. So, yeah. And I want to make sure.
Oh, you could combine them, and get a 1x1 matrix and then do the name that one.
1 by 1 node.
Mhm.
Technically a 1x1 matrix instead of a matrix.
Yeah, and so it's a question for y'all of, is turning both of these into current sources and then combining them and then turning it back into voltage sources, because that's how you would do it. And then you can find the current that way. Is that easier or is a MAME easier? That's super duper simple. That's up to y'all. So yeah, the other way to do it is,
On the name, would we can include the capacitor in the matrix equation?
You go with, impedance.
yes. Oh, that's another big thing. Make sure that you remember MAME, voltage sources, resistances, and impedances. Name, current sources, and admittances
Use it for general.
in general. if you have a bunch of things in admittances or in Siemens, even if he doesn't tell you it's gonna be a name, he wants you to use name. If he gives you things in terms of Siemens or admittances, or conductances or admittances. Same thing. If he gives it in terms of ohms, so resistances and impedances, he expects you to use a main. I don't know if it's a life hack or if it's a Russell hack, but I do not take credit for that. But yeah, so someone wanna either do the cute little meme or do a combination?
Are we finding the current and zero plus that order?
Just for funsies.
Oh, this is a 0 plus?
Yeah.
Oh, that was just like at T equals 0.
Well, okay, 0 and 0 plus
Oh, they're the same thing.
are the exact
Oh,
same
okay.
thing. And if you like reading textbooks, or wish to read a circuits textbook, you will see that it probably has different notation than the 0 minus, 0 and 0 plus. It'll probably just have two of them. It might just have 0 minus and 0, or 0 minus and 0 plus. It won't have all three, probably. That's from what I've seen in textbooks. What is that? 35 divided by 15. A gross number. Two point three. The 2.3. Yeah. And then 0.3 up. What is that? 10K in parallel, 5 and 15 in parallel. Or is it?
Yeah, I got 3.75K.
Yeah, that's right. I'm trying to think right now. So I'm trying to think of making sure that you would just add the impedances like you would do it complex.
What do you think about if we do the main?
No, if you just do it, I was trying to just simplify it down. Just make sure that it is like you would do the impedances added and then V over R is equal to current. V over Z, same thing. And yeah, I think you would, so. I don't have my. What do y'all get? Have y'all done it? Have y'all figured out the current?
Oh, yeah,
680. 680.
1.6.
Yeah, 2.650 then. I guess it's about like 3.75 there. So you treat the capacitor like a battery at that point, so you can add the voltage. And not another total. Resistance.
Yeah. And that's what I was trying to think of. Would you put the complex part in it or would you just do the battery? And yeah. You just add it like it's a battery. So to find the current, sure enough, 5 volts. How much did you get? Yeah. That looks right. That's what I got. Cause I don't know if you can see what I did up here. I did this combination, so the left side is 5 volts pointing up, 3.75. So y'all got. And then you connect it to the battery that we just got from the other side. Did that?
The KVL instead of the main.
Mm-hmm. Yeah, and that works. Like I said, it's just if you're more comfortable. So I reduced it down. That's how I did it. So I got 10 divided by 3.75. But same thing. You get it all 3 ways. That's the lovely thing about equivalences. But this was a tangent. That's how you, you see it?
Well, yeah, because you treat at time equals, yeah, at t equals 0, you treat the capacitor like a battery.
Exactly.
And then say if it's a battery at -5 volts, if it's pointing down, it would add up into the 5 volts.
Exactly.
Yeah, that's great.
You know, in
That's it.
class, he said, you wrote stuff out in 0, like just at time equals 0.
Mhm.
No problem, said there's a 0 plus. Those technically mean the same thing. Maybe not the same thing, but like when we do the equation, it's treated as the same basically.
Yeah. So if he does ask for the current, that's how you would find the current. You would treat it, you wouldn't use the impedance. You would treat it as a battery and you would find a loop and you would get the current that way. So question wasn't asking for that. But that is something that he could very well do. And again, for the inductor version of this, it's the exact opposite. So you can either find the voltage across it by reducing it down to a voltage source and a capacitor, or a voltage source and a resistor, figuring out what the voltage source is, or you could reduce it down to a current source and a resistor in parallel, multiply the current and the resistance to find what the voltage across is. Because remember, at time equals 0, you would do a current source and then a resistor. Yeah, because the inductor would be a current source and you would only be able to find the voltage across it at time is equal to 0. Exactly. That's the only time it would have a voltage across it that we can know is, well, generally, is that time is equal to 0, and then you use the current sources and the resistance in the rest of the circuit to figure out what the voltage would be across it. I'm speaking in a lot of, I feel like I'm losing people. Except you, you're doing good. He's over here having a realization, figuring out how it all works. But let's keep going. Let's do the rest of it, and let's figure out what the voltage is at time is equal to infinity. Okay? Do y'all mind if I erase? Well, I can actually just kind of change it. So originally this was -5. I'm gonna erase all of my extra work over here. So now at time is equal to infinity, how do we figure out the voltage?
Basically turn it into an open circuit again and leave the circuit as is for timing is equal to 0 plus. That was my insight on people.
Just pause before you answer.
Who made that suited?
What? Did you say?
Don't get.
Okay.
Chris, continue.
Okay, so what do y'all see? What's the voltage across it now? How would y'all figure that out? We basically have this. We have an open circuit here.
Transformations. First, you gotta get them all into current sources in parallel with the resistor, add them up, then another source transformation to get the equivalent voltage across the circuit.
Mm-hmm.
Voltage source point.
Mm-hmm. So
That ends up being about 5 volts, yeah.
So what I just erased is exactly what the work was for the next part, which is incredibly unfortunate.
Control Z.
Yeah, pretty much. So follow up. Remember how I said either way works? Since you're trying to figure out the voltage as time is equal to infinity, it makes a lot more sense to do the transformations to find the voltage because you need that anyway. So I am apologizing. Exactly. So
We just work both ways for practice. We need it.
I mean, yeah.
Yeah. The good review, we're going all the way in down.
there we go.
Every that is 1 plus 1.
Sounds good.
There's no such thing as 2. 2 is nothing, but it's 1 is nothing.
Two is a human invention.
Exactly.
You started this.
Continue.
So now basically we went from -5 to +5. And my computer doesn't want to let me reduce or go back and find all of the work that I just did, which is incredibly convenient. But what it
It's on the recording.
exactly. So what it comes down to is it's a voltage source and then this and then an open circuit essentially. This is 3.75 K This is 5 volts. So now we do KVL again. We have our plus and minus. I don't know why I decided red and blue, but that's what we did today. Yep.
Even if we don't want it, we we just, it's in our blood.
That's just.
In some of our blood.
Shouting out Mr. Keith right now.
Oh, red versus blue, yeah.
National students.
Yeah, we're Nashville, what the fuck you mean?
You're in the.
What's your fucking problem? Michael Moreno, who says where's Moreno?
Y'all, okay, calm down, y'all. Calm down. I started that. Apologies again. So we have 5 volts. Stop the conversation. Shutting that one down. Okay. So we have V1. So
Everybody shut up and pay attention.
Grace brought it up. man.
Michael.
y'all are
quiet.
killing
Okay,
me.
okay, she's trying to talk.
Yeah, just
Yeah.
listen.
Again, make sure V1 has the polarity of plus minus. So we know that V1 at time is equal to T plus 5. V1 at time is equal to infinity is equal to positive 5.
Wait, what?
Oh, good.
Oh,
what?
come on now,
Sorry.
get your shit together.
How was that? Wait. V1
Yeah.
plus is equal to infinity and infinity is equal to 5. Wait, okay. Okay,
Sorry.
oh.
Sorry. Those parentheses are
Yeah, okay.
important.
I was so.
Let me
confused.
this is probably a better way to write it.
Okay.
That's
Yeah, that's what.
so V1 at 0 plus and V1 at infinity are equal to negative 5 and 5
Okay, yeah,
respectively.
there you go.
That's on me. So yeah. How does everybody feel about that? Pretty good? Okay. That took us a while, but I hope that y'all can do it a lot faster now.
Grace, can I make it some good? I know that like, he was saying we haven't done 1.186 and obviously like you said, you might mix it up as well, but I think it'd be pretty cool if. I mean, this is just for me, I don't know if y'all could, y'all agree or not, but we work 1.186 together. That's a pretty big, I think, me personally think 1.186 is a pretty big one that you might put on the test.
Yeah, I
Because
agree.
it kind of combines everything,
Yeah.
and I think
That
that,
sure has a lot of concepts.
yeah, it has a concept that overlap
Yeah.
together, so if we could just like all work on it. and then-
Mhm.
I mean, if it's wrong, worst case scenario, you can always just shoot us an email Wednesday or, I don't know if you have the solution set to this homework.
I'm not sure. I can try to find it.
What if we don't, I mean.
What I can do,
We have it, it's just that one we got.
yeah,
I don't even know if it's.
I can look into it. The only thing, we can either do it after the review and we can do it on the whiteboard, or we can keep it on the review and I can just let everybody know.
Would you keep it on the?
Yeah,
keep it on the recording?
Yeah.
Because I think the rest of the ones that you're showing, we do have solutions. to.
Yeah, it's more just working them
Yeah,
together,
yeah.
understanding them, but
I don't think we're done.
we're not.
Okay.
We're not.
Sorry.
We're definitely not.
He shift, I shift. We did that like barely anything, like we had that one problem.
Actually, yeah.
Is that, did he say it might be on the test?
Yeah, you said it was.
When he said that, I'm thinking it's gonna be.
Because we only have like one example for each shift, and I think like one.
Yeah, yeah.
Two.
Okay. We can definitely do that. I have a problem that I can do.
Okay, yeah.
A vote.
It's 3/21.
Sorry about that.
These do take a long time, but at least like we have the solution, worst case scenario. But
Yeah.
for 1.186, like we done.
So really quick. VC of T. What's the equation?
Infinity line of plus. Big brackets, you see 0 minus you see infinity, close bracket, use the negative ceiling down.
Boom. We have all of those things now. I'm gonna erase all of this.
That'd be perspective, yeah. Yeah.
Exactly. So just to make sure that we have it written out. I know it's on the solutions, but capacitor is equal to be at infinity. And also, like, I put out my little cheat sheet. I have this written down as well. If y'all do want to use it.
You said it on this book, right?
Mhm.
Yeah. Thank you.
Infinity plus.
We don't have to derive this formula on the test, right?
No.
Okay.
Please.
good.
Please do not try to derive the formula. Plug it in and call it a day.
Right.
So what is the tau gonna be? What are she?
Oh, total resistance. At T equals 0 plus 4.
So what's that value?
125 microfarad.
That tracks. Sounds good. So we have all those things, we plug it in, that's the formula.
It's also looking to rise.
Yeah.
Yeah.
That's fine. Time, though.
Mhm.
Just basically.
Or if you want to solve the equation, it's you take the first part of it, then you multiply it by the percentage you're looking for. So you have like the constant in front of the e. You can multiply that by the percentage, and then you set the whole equation equal to that whole that you get, and then solve for time.
I like that, but tau matters a lot.
Yeah, but you forget it. If you forget.
The only reason that you wouldn't be able to do that is if you don't know what tau is.
Yeah, okay, that's fine.
So if you don't,
Throw that curveball. Curveball.
The time allotted, probably not.
I mean, and all of the ones we've been able to find,
Yeah.
how,
just saying that
Also,
would be the reason.
in these circuits, I feel like. With the circuits that give us, am I wrong in saying it's almost impossible not to find that? Like, well, you can find resistance and seasons and find the capacitor and one that's. Basically all the circuits you go.
Could it be a case where he can give us like a circuit, but not give us like the capacitor value instead of just give us the load capacitor?
That's fair.
And then that could be a whole can of worms.
But it's good to know the equation anyway, just in case. So let's look at 1.186. That's the one, right?
Yes.
Ooh, that's fun.
That does not look fun.
That's a fun one. Yeah.
But we have
So
4, 8, 9, 12, 15 body units, yeah.
before I go over this one, do y'all want me to do an E shift, I shift problem?
How do we do that?
Yeah, we did that.
Yeah.
We're already on this one.
You should, I should was not that bad. We just forgot to do.
So what he might throw on there is one where you have to do E shift and I shift in the same
Yeah,
problem.
that's a good. Oh, God. yeah.
Oh, wait, what? You should, I'm actually in the same problem?
It's not that bad, I promise.
Okay,
He did that to us and that's why I say it.
okay.
Just so when you think about it, think about how you would do both of them. It's not that bad, I promise. You just have to morph how you think a little bit. But what we can do is I'm going to do a snipping tool. And I'm going to this on my OneNote so I can have more room to write all of the things. Work. Perfect. Sweet. So let's think about it. How are we going to solve it?
Good to figure out. T equal to 0 minus.
Mm-hmm.
Because R2 is shorted and ETT is open, so it's simple. And L is short circuit.
So let's draw it out, what it looks like at t is equal to 0. We have our battery here. And then I'm just gonna draw a wire all the way down. Is everybody cool with that? These are terrible, terrible lines. But
Oh, we can tell what you're doing, so that's what counts.
yes, exactly. Mu V1. My computer's having a stroke again.
Try saying nice things to her, maybe my, that kind of better performance.
Um,
Someone didn't do first.
oh my gosh. What is V1?
Yeah, it's negative because of the polarity, but.
Okay.
Or the polarity given for B one.
Well, the voltage rise.
Grace, you tell them to calm down. Because they only do it.
Send them down. Okay. You okay? Okay. Yeah, V1. Yeah. 3K. We have 1K. We have simply a wire and we have mu V1. Mu is equal to 5. Can write volts per volt, but it's 5. Don't stress too much about the units. I know, like, he gave it at one point, he gave it Siemens, like he gave a mu in Siemens. And if you tried to do a name on that, MAME, if you tried to do like a resistances, you wouldn't also transform that mu. It's just a fun thing. A mu is always gonna, like, your constant is gonna stay the same, even if it's a different unit.
Yeah, it's just.
You're not gonna transform that constant.
Okay.
It's usually the same unit on the same unit for the chemical.
Exactly. But even if you were going to, you wouldn't have to. So we said we'll do a MAME. Easy peasy matrix, right? 1K, 0, 0, 3K. Is everybody good with me zooming through this?
You can do whatever you want to do.
Is that right?
Yeah, okay.
Is it just 5 and then
Yeah, because it was negative. It is with, current.
right, but it's like 5 and then 1K, 3K?
I see where you got the 5 from.
Yeah. Sorry.
You just, okay.
Skip the steps.
Yeah, I got it.
V1 is equal to oh, no. It's not 5. It is not 5 at all.
Oh,
It is 5K. Cause there we go. Yeah. Because V1 is equal to IM1 times 1K. Because you see that voltage across V equals IR. We have V, or no, we don't have V. We have I, we have R. Bob's your uncle. This is equal to 12.
On the polarity of that resistor, if you switch it, if it was plus or minus, would that be a negative IM one on that then?
Since the voltage rise.
So if it's since the voltage rise, it'd be a negative IM one.
Yes,
Okay,
Yeah,
just like.
I should change that. Thank you for catching my mistake. So it is negative 5K. Really?
that's what I'm thinking. I don't.
Wait, what- remember, we didn't have it.
Oh, well, he did,
We did, the previous one is similar, but.
no, he did 1.186 this part. He did, in class, he did T equal to 0 minus in class. That's what I have written down so far. And he has it as 5.
I worked with a negative.
Yeah, I mean, maybe I'm wrong, check out his notes, but I'm pretty sure he did.
It is very possible that in class Russell made a mistake.
Yeah,
Did he write?
yeah, I worked it out, so. Then you end up with positive and then you'll, for your milli.
Okay, so I guess you probably-
One,
I'm going off of him, so.
yeah, so it's a negative.
It's negative.
IM1.
I think it is a negative IM1 because of the polarity.
Just thinking about it.
Mhm.
You got two voltage sources going down, but the one, and that voltage source going down.
Yeah. And so, something you can think about is the voltage. Is going to be in reality, it's going to be a drop. Cause it's a resistor. But we're looking at it right now. In that loop, we have to have KVL followed. Hope it was helpful. It's all good.
He's gonna fail.
No.
Oh.
Dude.
He's a good guy. Don't say.
No,
shit like
okay,
that. He's a great.
shut up. So we have, it has to follow KVL, so we know it's gonna be a drop in reality. So we're gonna say it's negative IM1 because we want it to go the opposite way. So yeah, it's negative IM1, which means it's negative mu V1, which is equal to negative mu times negative IM1 times 1K, which is equal to IM1 times 1K. And then we subtract it over to the other side. So it becomes mu times 1K, which is equal to 5K. And move that over to the other side. Everybody good? Cool, good stuff. So what is our IM matrix?
Well,
No,
Oh, yeah.
just like solved.
well,
Yeah.
for IM1, 25.
Negative 25. Yeah.
Yeah, I got negative as well. But that was whenever I kept 5 positive. I don't know.
So yeah, did you change the positive and negative? Because if it's positive on the right side, we subtract.
Yeah, well, think about it this way, you got two voltage sources on both sides pushing through. Like, that current's gonna be going down the middle.
Yeah, so it should be a negative value.
That's weird, cause
Like, let me see your matrix. So,
he did it right. Make sure.
hold on,
I have in the full, right? 1 is 0.
negative 5.
Yeah, I think
It's subtracting negative.
Yeah, it's 12, it should be
Yeah.
12 positive 20.
So, yeah, so it should be in your final matrix, it should be negative 5 on the.
Oh, yeah. It makes sense because in reality, that voltage source is gonna be flipped.
Yeah,
Yeah, because the
Yeah.
current.
you have a negative 5K on the right, move them over, it becomes a.
You read that?
becomes a positive.
Right, but if you think about you said the current was gonna push down the middle. Since V1 is negative, the voltage source, that dependent voltage source is gonna flip polarities.
Oh.
So it is gonna be feeding the current around. Do you see what I'm saying? This guy right here
Yeah,
is actually gonna flip. So it's gonna be like that. You can't see that.
When multiplied by the, or the, one.
Exactly.
Because the, one is negative with polarity across the resistor. You flip the current, you flip the voltage. So you don't have a, negative 5K on the right? You do have a.
No, you do,
Yeah.
but I'm saying conceptually, this is
Yeah.
why it makes sense that they're both
No,
positive.
no, no. We don't have a negative, 5K on the right, it's positive 5K on the right, negative 5K on the left. Okay, yeah. So she was saying
If,
that.
if you understand,
Okay, I see, I see.
Don't
what-
worry
I
about
see what you're saying. I see what you're saying with the, yeah,
we good?
yeah, we good.
Sweet. Good stuff.
So positive 12, positive 20, what I got. Sound like that's right.
Yeah, is that what Russell got to, or did he get -20?
It was told -20, yeah, because originally the 5 that
Oh,
you had was
yeah.
positive.
I remember doing this on, I'm sorry.
Okay,
That's all we got to.
so now what we're trying to find is we're trying to find that current IL. How do we find the current IL? Boom, easy, right? Y'all see that kind of?
Yeah.
12 minus 20, which is equal to -8. Is this in milliamps?
Yeah.
Okay,
Uh,
makes sense. Makes sense. So at T is equal to 0 minus. Okay, this is sometimes what he asks for. That's, I don't know if he did that and y'all, he did this whole graph with the tau too.
It's in the problem.
It's in the problem.
Like this one, right?
You like that.
Oh,
1.16 we never had,
yeah, I think it was the.
but you can make a table for either one, for
Yeah.
each of them.
Yeah, exactly.
Before this, you had the table. Are
So-
you preferring that we have a table?
He might ask for it, so we're gonna do it.
Wait.
So the only difference from what we did on the last problem is you find tau for everything. So, yeah. Which we'll find tau in a second. So we have time equals 0, we have negative milliamps. So time is equal to 0 plus. Yes. And what's the voltage at T is equal to 0 minus? Indeed. Yes.
Quick thing. So on your matrix for 1K, 0, negative 5K, and 3K, shouldn't that 5K be positive because you're subtracting a negative 5K from the top? Because it would turn out to be -5 IM1.
No, because it's 5. It's positive 5.
Oh, we said that, we have stated that V1 is a negative IM1. When you do the main, on the right side, it comes out to a negative mu V1. So when you multiply, when you substitute V1 for negative IN1, it just becomes positive
Yeah.
mu IN1.
So you have the negative times the negative. So you end up getting 5 times IM1 times 1K.
Oh, I see.
So then you have positive 5K. And then you bring that over to the other side and it becomes a negative 5K.
Listen.
I see now.
Okay. My computer's having a stroke again. I have more than 40. It's bad.
Oh.
Because I have, it's a problem.
This is.
Oh, his computer like literally hard crashed yesterday in Polo One.
Like,
He was
see,
like-
this is one,
He just moved over.
this is one of them, and then this is the other one.
Oh.
Oh. We went over these times.
Turner is way worse. I think Turner's like sometimes you cannot even see them.
Yeah, well, I have two different, and I closed like a lot this morning.
Oh, my.
It's bad.
Oh.
It's all good. We're chilling. Don't worry about it. So, y'all, let's draw the circuit at t is equal to 0 plus.
Want us to be, we're finding the voltage for,
Zero plus.
zero plus. For the,
And the current, both,
for the current, we've already figured out.
yes.
So we replaced that, we call it inductor with a current source, correct?
Mm-hmm.
Since it's conventionally, would we have that just pointing down always, but since it's negative, we want to point it up or what? I'm just curious,
What?
like,
Like we got negative 8
Is-
milliamps.
is an inductor polarized?
Kind of.
Okay. So in this example, like, would we have our
I see.
arrow going down to start with?
So you're gonna have the arrow going down to start with because IL is pointing down.
Okay.
So the,
Since we had, since we had IL with the IN2, IN1, since we said
Mhm.
we need IN1.
because this guy is pointing down. So that
Oh,
means we're solving for a current source pointing down.
Got it, okay, let's see.
But because it's negative, it's actually gonna be pointing up.
Dependent or independent?
That could be independent. On the things that we've done.
Yeah, no. You're totally right. I just drew it wrong. Now, what do we do with this? Do you want to do MAME or do you want to actually, yeah.
And then you could just, what is it, isn't,
We do that one, 3 by 3, but yeah.
isn't the voltage across that just the resistor in that line times the current we get? Could be wrong. If we
Wait,
have,
say that again?
so if we have the same thing as an IN1 this way, IN2 just going this way,
Mm-hmm.
the current across that inductor is gonna be IN1 minus IN2. We can find the voltage for that, if we just multiply it by the resistance in that.
It's probably asking us to write out an equation for I since L P, right? Skip through, we already know I L and zero, both
Actually, you're right.
relevant, and just go straight to T.
No, so we're trying to, we're doing that tape. It's not asking,
Yeah,
but
we're doing the same.
we're acting like that.
Oh,
So we're trying to find it. Yeah.
Mm-hmm.
So it just went 0. Like what you say, 0.
Didn't you say we just turned off all the current sources? Or all the sources and just add up the resistance? Am I wrong in saying that?
That's whenever it comes to like our equivalents, right?
Yeah.
I think
Technically, we can find our, equivalents and just, we know the, well, never mind.
well, because we're trying to find we're trying to figure out the table, we can do it like that, yeah.
Would we need to transform that? No, I don't. I'm gonna
But
say
the question says what, 0 plus only, right? Or is it 0 minus 2?
0 plus is negative. But she's acting like if that table's been given, we're trying to find voltage and current
Yeah.
at 0 plus or 0 minus plus.
And he did solve it for 0 minus anyways in the beginning. And then he was gonna go on to 0 plus, but then he stopped fast. So, because I was doing this problem on my own and I got stuck because, well, 0 plus, we close the circuit to make it look like top right. But then obviously we have that EG2, which is a little bit different.
Mm-hmm.
And then even then, whenever it comes to, let's say we get everything done with the 0 plus and we go to infinity,
Mm-hmm.
that current source would be a voltage source, right? E naught.
The current source will
like-
change to a short at
Which-
t is equal to infinity. Right?
Okay.
Because it's an inductor.
Was a capacitor that could be, you know,
Oh, that's really good. I mean,
or it'd be. That's what I was confused to.
So at infinity, inductor will always be a short circuit and capacitor,
Oh, wait.
actually,
What
no.
he did was he shorted it and put a battery in knob with 1 volt. I think that's what it was.
It might-
For,
Opened it to try to find, if you have the solutions for this, I think it's the solution for the prior example, so 1.182. It's a completely different, question, but the
Mhm.
steps are the exact same.
So whenever he went to t equals 0 plus, he went and made it to a E naught. It was a 15 quick one. I gotta have the account. This quick.
the different. Does that one have a sinusoidal though?
I think it did. This is the only one that we have assigned.
Yeah, that's
Oh.
that's what I just realized. So at t is equal to infinity, it's not going to be steady state.
We have to do, then,
Exactly. You're gonna solve for at t is equal to infinity.
yeah, that part was all good.
So
So I think like for this question, it's just harder to do the table. I couldn't run that.
yeah, but the 0 plus is harder.
I mean, because he was gonna solve that 2 in fast, because we wrote down t is equal to 0, but no, not at the time.
Yeah, so what I'm trying to think of, and this is the part where I have an idea, but I don't know for sure.
Find the voltage at 0 plus or to do what I'm saying.
So the current at the current at, oh, no. Okay, yeah. The current at 0 plus is 8 milliamps. I was trying to think, the voltage at 0 plus is weird because what does a sinusoidal voltage source look like the moment it turns on? Yeah, but exactly the moment it turns on. Does it?
If it's, well,
What's
if it's 9, it's a great line up. I mean, a 0 would be 0.
Yeah.
Yeah.
So it would be 0. But I'm not sure. Hypothetically, it would be 0. Unless, but it starts at cosine. So would it start at 5?
But also, isn't t equals 0 in respect to a switch, not to the source?
Well,
Yes.
like,
Well, no,
the switch
because
is like, isn't the switch directly related to the source too as well, like this?
Oh, I see,
Yeah.
yeah.
Well,
Yeah, 'cause-
if we do what I said, as in think of time 0 and time 0 plus as the same working problem, 0 plus, there will be a voltage.
Yeah. But the question is, does it start at 5 volts or does it start at 0?
Oh, it starts at,
I would think if it's at 0 plus, it theoretically, like you said, I think it was 0.
But it's a cosine, so it starts at 1,
I would
right?
say 5. That's how I do it.
That's the part I do not
I'm
know.
just as like, and I emailed him hoping he post a solution, but he never did.
Yeah, so he might just not solve for the voltage.
I mean, for this one.
If for some reason he gives you a thing and he gives you a sinusoidal voltage source and he asks you to find the voltage at t is equal to 0, write down any assumption you make. So if you say you assume that it starts at 5, write down that and then solve it. If you say you assume it starts at 0, do that and write down that.
Oh, so you're saying we should get extra pocket credit for it just by doing that, right?
I'm saying if for some reason that gets put on the test and
Because if I was Russell, I would put something like this on the test for sure, because it has like sinusoidal, it's
It
like,
has everything.
it kind of has a lot of everything.
Yeah.
So that's why I like,
And for sure, at time is equal to the current at time is equal to 0. That's good. The current at time is equal to infinity, that's good. It's the voltage, that's the question, that's weird. The voltage at time is equal to 0 less, but that's not being asked for.
So we did not a similar problem, but we did an example with sinusoidal stuff. And at 0, at time equal to 0. This was with the capacitor. Capacitor. He made that capacitor just 15 volts. If we started out our EG two, or the current, the voltage source was 5 cosine omega t. And then when he went to time equals to 0, he put 15 volts as that source.
Kind of how
As
you
that capacitor.
So how you did it, so 8 milliamps is correct so far, like, putting it in there.
Yeah, so 8 milliamps is correct. Like I said, it was just looking at what the voltage is at time is equal to 0 plus.
Well, would we not do something similar for just the same thing with the battery? So that didn't meet, I'm sorry, not the capacitor, like it was straight up a voltage source that was sinusoidal. It started out as 15 cosine omega t. When time equals to 0, we just had that 15 volts for that current.
Oh,
voltage.
no, cause it's omega t, that's 0. Of course it's.
I don't know if it's still here.
Is that one right there?
It's a black table.
That
No,
one?
it's a charger.
Oh,
No, it's not.
What type is it?
It's a USB to.
Is that giant?
No, it's not that one.
Oh,
No.
That's ours. No, I don't see it.
The other one.
There wasn't anything on the table. so we got-
That's where.
What about this big?
Alright,
It shouldn't be that one either.
Sure.
That's okay.
Oh,
yeah, no, alright, no worries.
So we were overthinking this. You plug in t is equal to 0. What's 15 cosine of 0? 15.
Okay, cool.
So it's 15. Yeah,
Well, for this one, it would be 5. The example. I
Yes.
was talking about.
yes, it would be 5. So
For when you get to T infinity. Right, yeah, we put it
And 0.
0 plus.
She's saying when
Yeah.
t is equal to 0, cosine of 0 is 1.
So it was when you flip the switch, it goes straight to
it's
sine.
straight to 15 because it's a cosine,
So if it was
which
sine-
makes sense.
If it was sine.
It would be
then it
0.
would be 0.
Exactly. That makes sense. Like I said, I'm thinking through this with y'all.
So then we have to take out that 8 milliamps and put it.
So the example that we kind of stopped on, we were just trying to find the voltage at 0, I'm sorry, yeah, the voltage at 0 plus.
Mm-hmm.
And then we were confused on the steady state thing, so now we're going back to that.
Yeah.
So
Mhm.
when we're doing the current stuff like that, can you just treat it like a, or should we put it in? Before what we're doing, should put that current source back in.
So at 0 plus, if you're trying to find the voltage. Yeah. So then from here, you can figure out what the voltage is using this, because these are all constants now. So if you were looking of the voltage from here to here, you could solve it using a MAME or a name, depending on whichever way you want to solve it. It wasn't asking for this, but this is how you would solve it.
I'm gonna be so happy in something. So happy.
Yes,
If we did main, right?
yes,
And find, would we need to transform that?
yes.
Okay,
So if you did a MAME, it would actually be a 3x3. If you did name, it would be a 2x2.
where are the nodes technically would be?
The top and the
Should be
bottom.
3, or no. There's one
So-
in the middle and the top.
So if you did it, it would go to this. So
Wait, wouldn't you first need to? You could also transform that voltage source into a current source, right?
I think name's easier, like, name definitely would be easier. Yeah.
I think that was just in series, which I currently my system doing.
it might.
Like any of the,
But if it's name, you can just combine that current source, independent current
so
source.
under main is voltage sources, right? How you gonna?
Main is the current source.
Yeah, oh wait. Main.
Yeah, main.
It's voltage.
Yeah.
So how do you transform that middle current source into a voltage source? You can't, because it's in series with a resistor, not parallel.
That's true.
You have to use another. You have to do that?
Yeah, you can have.
Yeah. Okay, that's good, that's fair, because then you would have, you'd have to. Isn't, yeah. I mean, it's probably.
So you could do name. So what you would end up doing is, oh, you still couldn't even do that. That would be so weird. So what you could do is you could have your nodes. This is your node.
That's probably the only note.
Yes.
Ground would be at the bottom, right? We have the ground.
Oh, he does some of these like this in circuit 2. So here's what he does. So he does, this is node 1, this is node 2, and then this is ground.
Got enough.
Alright.
I've seen on the test boys.
Bro, that's on the
I'm gonna take my mental load, bro. Oh my God.
So
Really hope we don't add that.
it looks gross. It's not that bad.
That bad. It's
Just
just the
name.
it's placement of the node that's just kind of.
His name.
Exactly. It's just name. So this, I'm gonna do lots of circles. This, and this are all shared between node 1 and 2.
Right.
This is only node bottom, and this is only the node of the top.
Oh,
Okay.
It's actually not that bad.
It's not that bad.
okay.
And seeing a ground in the middle,
It's just weird.
it's weird, but it's 100% something you're gonna see in circuits too.
I think that happened on like the second.
Yeah, it was with name. We had to do with name and
Yeah.
display, or even the problem sets.
Yeah,
They gave us-
Yeah.
Yeah.
So
Was it the February?
It was a big one.
that's how you can do it.
We've had a couple like that.
So basically, probably not going to see this.
I don't know. He's.
At least where you need the voltage. So then, okay,
I don't know.
follow-up question. What's the voltage across this?
Yeah. Because.
No,
No,
it'd be node
one of the notes with the ground in the middle.
Yeah.
Oh, yeah.
Use the top note. That's it.
It is just the top node. So that's how you would solve it.
I don't think we're gonna see this
But we're
one.
getting free circuits too now.
I don't either, but the idea that from the node to ground, that was something that was on test 2. So that's helpful.
Oh, so so if you're,
Oh, that's right.
going, you don't just open down because it's going, because don't. Oh,
Because in the actual homework, it only asks for 0, but it asked for 0 plus, didn't it?
But I didn't ask for the voltage. This is how you would find the voltage, not the current.
Yeah, we're just making it harder for it.
Yeah.
We are making it harder for ourselves, but this is cool.
It didn't. and like,
That's cool.
Now that we're my understanding.
yeah, why-
default for, the top node, right?
Kind of. So you would do the name. So you would write out the 2x2 matrix, which isn't too bad.
Okay.
And then, so you would do the matrix, you would subtract the dependent sources.
Okay.
And then once you do the inverse, so once you solve it, you would find what VN1 is, and then that would be the voltage over the inductor.
Okay.
If,
If you just did a 1x1 with the, since like technically you don't need to.
but then here's what would happen. Well, yeah. Kind of, but you can't do Ohm's law for current flows. So then you would find if this is the ground, so this is why I did the ground here. Because if this is the ground, well, that's weird. Then you would know the difference from this node to this node. Well, yeah, it could work. Yeah. And then you would just have to subtract the voltage over this, which is equal to the current times the resistance.
Oh. Interesting. Isn't that a bit of
So
a-
yes, you could do 1 by 1, but then you would have to remember to subtract this voltage from VN1
so basically an extra step if you did that?
minus R times 8 milliamps.
Oh, so this is just,
No.
Does that make sense?
We're lucky for this one.
Yeah. Yeah, so like I said, this is all just extra work. I think it's kind of cool.
Do we have to figure out the current for
Oh,
infinity
okay,
as well?
that makes
Yes, we have to figure out the current for infinity.
Infinity or no?
Wait, no,
No, like a zero plus?
what? What?
I thought it was infinity.
Yeah, I did it when I designed it.
But no, because you need the time domain expression.
So the only thing that it's asking for, the current one is at 0 plus will be the whole thing.
You need current for infinity for the
Wait,
equation.
When it comes to infinity, that circuit will be. We have that inductor as a short,
yeah, that 4K
Mhm.
involved.
that 4 kV involved.
Maybe to even involved, and you scratch out the EG.
Now the EG. No, we would use that actual expression, right, whenever we solve it,
We need actual.
because EG 2t is equal to 5 cosine omega t.
Correct, but like I'm
Make it
saying,
like
I'm
that.
saying, the EG 1 of 12 volts, that's no longer valid, that's outside the circuit,
Yeah.
but that's now open.
Yeah, so your quote unquote infinity is still gonna be a sinusoidal.
Yeah.
So like they said, what you do here is you take what we just did. Except you do this, you get rid of this. Becomes short, no, stop. Okay, it becomes a short. Oh, yep. Okay. I really do not, worry about it. It's fine. Frustration.
It'd be short right there.
Mm-hmm,
On that side, it'd be.
the sinusoidal. No,
Well, that's what I'm saying, yeah, it'd be the.
Oh, wait,
expression. It'd be the
at
expression.
infinity? Well, then, yeah.
Try petting it. Trust me, whatever they try to happen, sometimes I know it's silly, but it works.
I just use percussive maintenance.
Uh,
Yeah, it's hitting it until it works.
uh,
That's a bit harsh.
Percussive maintenance.
You,
That's like an actual term. Like that's like you can Google that and that's a thing.
Cycle power to the main.
Oh, it is?
Yeah,
Amazing.
no, I didn't come up with that. I'm not that smart. Not that good. Okay, but you get my point. My pen isn't wanting to write right now. So now you do the main, right?
Yeah.
Yeah.
So maybe what is it? 5. -4 and 4 and then 3.
Mm-hmm. It's just the pen at this point. That's not working. That's okay.
You have a review session for circuits too?
I don't know.
Confident that there's.
It's on the 10th. So everyone's just
Oh.
we have 3 finals before then. Like it's next week on Wednesday. So circuits 2 is kind of out of sight, out of
Wait,
mind.
are you reading that, right?
Not anymore.
Okay.
You're good. So what's the main? Is the pen gonna work now? Okay. My pen is not working. That's the problem. One of the problems. Maybe. But let me draw with touch. Okay, there we go. Hurrah. what are the values? Five, -4.
Yeah, that's what I got. And then that 15 cosine 30,000 T. Oh, I'm sorry, 5 cosine 30 KT.
Which becomes 5, right?
Well, we have to put it into rectangular form, right? We have to put it.
5 plus,
0,
J
0.
Yeah, 5 plus J.
Well, you put it in phasor form, not rectangular form.
Yeah.
Yeah, you're good. Just making sure.
Phasor form is the 5 plus J, right?
Yeah.
Yeah, yeah. Yeah, yeah.
So what is it? 5.
5, like,
Now it's
angle type of thing.
yeah,
And then 0.
yeah,
Is it 0?
yeah.
Well, because there's no cosine.
There's no phi in the problem.
30, okay. Oh, no, feeding, right, you're right, that's where that.
Yeah, that's.
Mm-hmm. So that's just 5, right?
And I guess like the bottom part would be 0, and then we have to bring over that. Would be 1 would say, negative or minus.
Yeah.
So was, oh, we already said,
5 on the right side.
yeah, positive. Negative.
Really quick.
-9.
Go home, we can put everything down first time.
Can y'all hear the fans on my computer? It's
Yeah, I can
honestly, my little Surface is crying. It's not old, it's just I'm
You
not
put a-
using it the way that it's supposed to be used. Yeah. And also like it's running a Teams thing and recording
Oh,
and
yeah.
transcribing right now.
Yeah, Microsoft Teams especially takes a lot, like,
No.
it's 60 hours.
You good? I don't know, but he told me not to use it, I can't use it. I guess I just have to. do it. No, it's fine.
Where's your calculator?
Would you help? Huh? I got robbed that night.
Where's your
Are
calculator?
you serious?
I got robbed that
Where's your
night.
calculator?
I got jumped.
Where's your calculator?
I didn't see.
By 2 who had
Jump for it.
beat the crap out of it.
Did I not? Or?
Thanks.
Yeah, I just wanna know where your calculator.
Hey, Grace, when I'm mean, you tell me to stop, but when he's mean, just let it go. Let it go.
Y'all, what's the answer?
Where's your calculator? Where's your calculator?
Yeah. Where'd you at? -35, -45.
That's what I do. You're pretty fucking.
Milliamps?
Yeah.
Those are nice numbers. So IL is IM1 minus IM2, right? Equal to 10?
What is part B is just the expression, right?
Yeah, we gotta find Cal. I'm sorry, we gotta find people when resistance and induction.
That's whenever we turn off all the
Yeah, that's what I'm thinking.
switches.
Mm-hmm.
Dependent.
But-
Yeah, but-
It's the home, right? I think it's called, so we just have resistor guy. Or conductor.
But this is sinusoidal.
Oh,
So,
I didn't. Oh, so we need the inductor in there too.
well, that's not my point. The point is that the current needs to be in form of like cosine.
Oh, okay.
So,
And cosine.
Yeah.
30 kV.
Oh,
and that's at time is equal to infinity. So,
For this one. At t equals 0, we don't have a sinusoidal, so that shows that.
Yeah.
Equals to that.
Are we gonna, when we have the full-on equation, we're gonna wanna have them in similar form, right?
yeah, what were you saying?
Because we didn't have a sinusoidal voltage source of t equals 0,
Mm-hmm.
that part is just gonna be a, exponential.
For the expression.
Yeah.
I'm shaky on this part too. What's it gonna equal? Well, let's do the time expressions
Can you do it for geometry?
for the
So when we did it,
time
when
expression.
we kind of did it in class,
Mhm.
like you have your transient slash homogeneous
Oh,
part,
right.
and then you have your steady state part.
Right.
Like the first part, the transient part will be your exponential, and then your steady state will be a cosine.
Why?
But I mean, I don't know.
Why? Because YP, why particular with the sinusoidal rate?
Yeah.
Well, technically in math terms, it's YC plus. YP.
Yeah,
Why, I think you said kind of the particular is the sinusoidal.
correct.
Yes, for this problem.
Yeah, we have, cause
So
we
that's
had
your steady state.
the total, we did it
Mhm.
in voltage, so like the steady state, it was just the, that low voltage transient, and then the T tau plus the sinusoidal part.
Yeah, and that's the same as I at infinity plus IL of 0 minus IL infinity times e to the negative t over tau, right?
Wait, so I mean. contribution.
No, you're good. The final thing is gonna be, that's all I said. That is the
Okay, so it's just,
genius in the particular, or the, yeah.
right, so it's
Right.
it's just like the capacitor voltage.
Mhm. Sexy.
Would not be able to hear
It's
that.
just, of course.
It's got
Yes. Okay, so. Put it all together, right? So let's
You don't need it.
you kind of need it. What's tau? Oh, okay. Yeah,
E times,
Admittances to.
B times L,
Well, it'd be,
or or L over R.
like, we would find tau, we have to find the resistance equivalence, but obviously like at T, the circuit for 0 minus and T infinity are both different. So like, we would find, but we would find the tau at infinity though, right? We have to.
Yeah,
Yeah.
yes. Now, question, is the we turn off all the I'm sorry, all of the sources, correct? As into where we just have the resistors, or do we also have the inductor or capacitor?
But I think for T infinity, we won't have to worry about the inductor because that's shorted for infinity.
Right,
Yeah.
got it. So it's just the resistor.
Yeah, so it's just, so they're all in, I guess you could say parallel.
Yeah.
No,
R1 and R3 are in parallel, and then they're in series with R2.
wait, what?
Well, because it's like.
Yes.
Yeah, I'm gonna mess up the numbers there, but.
Well, 'cause now.
Uh,
Sources, they're parallel. They're still.
Yeah, you can take them all parallel.
Yeah, they're all three of them parallel. So you got them up on parallel.
I mean, it depends on, well.
Well, I mean, that's assuming I'm right.
Just put them in a one loop. What I thought was, what is it, the right to parallel, and you just might as well put it in series, but that's how we kind of try to.
what did he do?
Yeah.
Did you say that he did,
He did like a full.
or, but
Yeah.
what did he do with the sinusoidal? Did he make it an open or a short?
I don't know, we didn't.
I don't know. I don't think we didn't get to that far. Yeah, we didn't get to, we only finished T0 minus. and
Oh, I thought there was one before that where he did a sinusoidal.
Oh, we used the same part. We literally just got to the equation and we literally said RC or tau, or just count. Like, we did not find
No
equivalent.
back here, there's no back here. You can show that picture.
But it sounds like, based on something.
Oh, yeah, we didn't do it with the sinusoidal problem. This was the only one that he did.
But I mean, if we just have those resistors, they'd be, one of them, we put in parallel with one side and then they'd be in series, right? Because if it's not, then it's.
Yes, but the thing that I was getting at is a sinusoidal voltage source. Is that a short or is that an open?
Well, it comes out. Yeah, because we're trying to find our equivalence. for tau. And that means
Mhm.
shut off all.
I understand.
I know what you mean, yeah.
Door open, but shouldn't just all voltage sources be, shorted, no matter if it's steady or,
Unsteady.
sinusoidal?
Because whenever Russell was talking about it, he never made any, he never said anything about an exception. He just
Yeah,
said
I'll
that
agree
you
with
turn
that.
off all sources.
But,
You still turned it off. I just,
well, no, she's trying to act, if it's gonna, she's trying to ask if it's gonna be open or a short. And I'm saying that
Like probably a short,
should, voltage sources should all just be short,
because
current sources should all be open, period. So that's my thinking. Yeah. I have no basis on that. I'm just thinking like that.
what do y'all think over there?
Yeah, what do y'all think?
Should that voltage source be open or closed? Since, I mean, open or short, I'm sorry.
Well, see, the most way, I remember one of the problems he
I don't
put
remember that.
it was a problem like this. I don't remember exactly what he did, but he opened it up, put a source in, and then did all that. And after that, he just had it shorted out
Way-
after that.
Right.
But I think if someone has that written down, check
Think
that.
about it this way, if you're trying to get, test the resistance through something, you turn it off first,
Yeah.
right?
Yes, you turn it off, but like when a turned off current source is an open
Yeah.
and a turned off voltage source is a short. What I'm
Yeah.
asking is,
If you're trying to get the,
what I'm asking is a sinusoidal voltage source. Is that an open or a short?
I-
why?
Cause I think it might be.
On
Open.
that
I
last
think
thing,
it's an open.
he put, instead of having the inductor there, he put, I'm sorry, the problem that I'm looking at because of the, we have the password.
I think it's open because if you think about it, a DC, a capacitor inductor is,
That's what I'm thinking.
yeah, so I think it open makes sense.
So then I guess if it was like a sinusoidal,
Oh.
Cause there's not current flowing through it.
For a previous example on this problem setting of like 1.192, looking for G equivalents, you put a, what do you call it? You put a 1 volt battery in place of, I don't know if it was a capacitor or an inductor, but just put that.
he had like a.
After you opened it,
Yeah,
and he put that in to do the whole thing to it.
But that would,
Since it's an inductor, it would be the opposite.
Yeah.
It would just be an open still.
yeah,
So
Say that
that's
again,
the reason that he put a 1 volt source in for the capacitor was because it acts as a battery.
correct, got it.
It would act as a current source, so it would just be an open circuit.
Okay, see what you're saying.
The question still is, I feel like I'm not sure, and this is the stipulation. I feel like a sinusoidal voltage source is going to open when you're trying to find the resistance.
can ask
Yeah,
David.
but-
We can have David.
Really?
You know, another
You don't
thing
have Dr. Russell's number?
for,
Well, he's probably asleep now, all right?
Yeah, he's asleep.
It was probably.
That's still insane. Everybody's healthy, but all the time.
Crashed out.
At the same time, it doesn't say anything specific about flying tau. It
Yes,
says
but you need
flying-
the voltage, the current expression list has tau in it.
So how much points would we get off if this was a test question?
Not much.
Yeah.
Not much.
Let me
You're
see
fine.
that example with the voltage source connected to the open.
Oh, actually, let me get some.
Yeah, I mean, we never had an example like.
This is, again, kind of wild if he puts this on the test.
Well, he's a wild man.
That's true.
He is a wild man.
So when we did this, a similar problem like this in class, the expression just had tau instead of actual value.
Yeah, he didn't finish it all the way. He didn't put it.
There you go, just put tau.
That's. what-
That's easy.
Yeah.
Wait, we're this far. I mean, why was it just? Damn, it's just one single. One
Yeah.
parallel.
The point is, okay, let's do it this way. If it is an open circuit, then you combine the two in parallel and then you add it in series. If it's a short, you add them all in parallel.
Sweet.
Worst case scenario, you just miss half the credit. Half the credit.
That would be a very small point off. It's one of those two. I'm not sure which. I will look into that and figure that out.
Okay, and then once we we can just put tau, then I guess for now. So
Yeah.
when we get to the full expression, it'd be. What, is it I out of,
It's coming. I'm the same.
like the left side of the expression? I forgot what he used it as to define with the homogeneous and like the, like YSC and Y particulars.
I'm gonna do my
It's
question.
still just I of infinity plus bracket I0 minus I infinity times E times negative tau over T. negative t over tau. So that's, you can call it particular homogeneous, you can call it transient, you can call it steady state. There's like a million that are synonyms for
I
it.
might put them on the test too. Like,
He put like, no, I don't think, he gave us like 10 different names for each. I've written down.
Yeah, there's also the singularity. There's all of them. He gives you a table in circuits 2 of all of the synonyms for it. But 10 cosine of 30 kt plus bracket of 8, but you would need that to be an exponent, right? What's the exponent version of it?
It's negative t over tau.
No.
That's exponent.
Huh?
Exponent version of what?
Negative 8 milliamps. What would you put there? Is it just negative 8?
I'm basing it off of the notes, based on what he
Negative
did.
8 milliamps, wouldn't I don't know what you mean by exponent.
I also know explicitly, basically what I
don't know, you
Negative
have-
8 e to the negative t over tau plus 10 cosine 30 k t, based on what he did from that,
Yeah.
Yeah.
example in class. It's,
Yeah, that's right. From what I think.
Okay, cool. That's easier.
Well, wasn't,
that's,
Yeah, I
that's
guess
not
so.
exclusively how he did it. I don't know if that's what he did wrong. He literally just had like IL equals K1 e to the negative t over tau. He just said that's the transient part. Plus, IM cosine 30 kt plus b divided by phi, and that's the steady state.
So he didn't solve for the constant, he didn't solve for I max, I guess. Well, yeah, so that part, the 0 plus minus 0 infinity is,
Oh,
that's the constant.
yeah, that was something like. I remember him doing something
Right.
like that, but I don't know if it was like anything similar to this.
So this one was created.
Yeah, this one's kind of wild, but full and complete time domain expression is what it's asking for. So you need the whole thing.
oh, so what he did was he just said, we knew that, the voltage at 0 for, found the voltage, so
Mhm.
for this one, the current at
Yeah.
0, he plugged that in and then found, whatever K.
I think that's what I did.
Yeah, because that whole thing is gonna end up being.
Cool.
Yeah.
So that was a lot.
How's it work?
Not on the test.
Minus 25.
Go for it.
That took us like.
Hold up, y'all. Yeah, no. Not like this.
But,
I-
giving you problems like this, problem sets and stuff like. With, or did that not?
Like, okay, in the past, he's done second order before,
Oh.
but y'all aren't having second order.
Right.
So he kind of changed, starting in like 2021, he changed all of what he did. So he's giving different, like he used to do op amps, so that used to be on the final exam,
With your case one?
but
Sorry,
that's
please.
obviously not the case anymore.
The Bill Harmon chair.
So.
Yeah, today
Mhm.
today he told me
No, so question, when you were taking circuits, did,
No,
sweet.
I just laughed.
no. If this is on your test, I am really sorry.
Let's go.
No.
Technically, like, this whole semester has been Bohemian, so, like,
fine.
Yeah, the fine boat beaver.
bend over, here it comes again.
Y'all.
And.
Okay, y'all.
Let's go.
Y'all, do y'all want to do an E shift, I shift problem?
Show us the one where it's 2. Show us the one. with-
I don't know if I have that, because that was the,
Let me just open up another.
don't do that.
All circuits.
I was wondering where y'all went. Y'all are just studying for the final.
Yeah, we are.
Let's ask him the sinusoidal
No.
Sorry, correct?
Oh my gosh,
Yeah.
that's rough.
You should that.
In monies. Right.
I don't think I have it.
Had my hopes up. So, I was like, that's gonna be cool and.
It was on the final exam and he doesn't give out the final.
Yeah, and I'll put it all together, and organize it.
We did together.
Or only one person.
What I do have is this. So what I'll do is I'll just kind of go through it really quick.
Oh, okay, this is from policy one, right?
Not this one. This one's different.
Oh.
So,
Trying to get rid of note two, it looks like. Or no.
a little bit. So what you're gonna do is, this E2 right here, is my pen gonna work now?
Wait.
Yes.
That has to be in series of R4, or is it in series of R, what is that, on the top? R3? Is that R3 on the top?
Mhm.
Okay. So you, wait.
So-
do both ways, like, put it in series of R3 or put it in series of R4?
So, no, you have to do both.
Oh, both, oh.
So-
Yeah.
So what I'm just gonna show you is the solutions, because this has been going on for a while. So he takes this, these are both by themselves. Voltage sources without resistors are a pain to deal with, so we do E shift and I shift. And now if you remember, what we're gonna do is we want to push it out. So we take this voltage source and we push it through the node and we push it, that means it's gonna go up and it's gonna go down, which means that the polarity on this side is gonna be up and this side is gonna be down. Does that make sense?
Yeah, that makes.
But it would be the same value for both.
Yes, yes. And then on this one, same thing. It's gonna get pushed up. So now we have a voltage source here that's like this. And then we have a voltage source here that's like this.
Oh,
The
that's not good.
direction of where it goes depends on where the positive node of the battery is.
Yes. So now
Too bad.
all of the voltage sources are in series with resistors, so you can transform them into current sources and reduce it down from there. So
Could you do me?
the point is to get it to look like this.
Right.
So the
Oh.
point is, the question is asking to get it down to one current source and one resistor. So
Oh.
Grace, it's been a while, but like go back, like we can go back up. to this.
Yeah.
If we were to like, if I was looking at it, we would have put like this for just pushing that left side voltage source through node 4. Could we can push it through a ground, right? Like it wouldn't matter at all. Because I don't know if you said like it's been.
yeah, no, that's fine. You can do it either way.
Another question. You can take a screenshot of this and upload it to Discord. We can have it. Like I'm just.
I think we have, E
Mhm.
shift, I shift, like.
Yeah, but it's.
Yes, I don't. Yes.
Or is it because it's through Discord?
I'm gonna, okay, I'm gonna go ahead. I think that we are pretty good, only 2.5 hours.
Or what, 2 problems?
But,
It was.
so, I'm gonna go ahead, I'm gonna stop the recording is what I'm gonna do first.
Gonna talk after.
One guy left. There was those two guys that were left.